Uh, Hello, everybody. I hope y'all can hear me well. So today I will be presenting this paper, ImageBind, one embedding space to bind them all. It is a very recent paper, so it was accepted to CVPR 2023, and it's it's among the highlighted papers in CVPR this time. So um, okay. So now I want you all to look at this image. And now when we look at this image for a while, and when we see the beach, so when we kind of like, you get the sense of like the waves crashing softly, and then this looks very calm, so probably there's like a very light breeze here. And then when you keep looking at it, because of the suns, you're probably feeling the heat, and then the soft sand on your feet. And so when you keep looking at this, you'd probably sometimes would want to write a poem about it even. So that's basically so this is just one image, but it's you can feel that it's activating all your, like, some of your sensors that basically connects with the different features of this image. So that is basically the key idea of this paper. That is, that's showing that an image has this binding property, where basically that so that, you know, like which enables many sources to supervise, to learn different features relating to this image. So basically that happens by aligning these different sensory experiences with the different features of this image. So in a technical sense, you can basically come into like a single embedding, a joint embedding space, where you are able to learn visual features by aligning these sensors, the information that you get from different sensors with these image features. So now in this paper, so the core is the image, and then they're basically focusing on different other data types, like audio, text, thermal, and IMU and depth information. So essentially, like, what they're saying is, if you can align these different data modalities with the image features, you can basically come into a single, like a joint embedding space. Now, in order to achieve this, from the machine learning sense, you would need to basically, for this scenario, this phenomena, to achieve this in a machine learning model, you need to have paired data with all of these types of modalities. Like, for the same image, you need to have a pair between audio and image, and then the text and image, and so on and so forth. Now, this is a problem because it's actually quite infeasible to have an image which would have pairs, corresponding pairs with all of these other 5 data types. So so therefore, these authors, they are basically showing us a way where you could learn a joint embedding across these 6 different modalities, that is image, text, audio, depth, thermal, and IMU, with only image paired data. And they necessarily don't need to have a pairing with all of the other data modalities. So moving on, before we go to see their approach, let's look at the related work here. So here, when it comes to learning about joint embedding spaces, there have been many work where you look at languages, language and image. Basically, there are models that train images with language signals to do tasks such as open vocabulary recognition and text-to-image retrieval. And for some examples, this Clip, Align, and Florence, these are 3 types of models where they take a huge amount of image text pair data and train models to embed these inputs into a joint space using contrastive learning. Now, when you these type of models, so they can so given a text, you could retrieve different images, and even zero shot, like you don't need to have all of the types of classes within your text. So, but the issue in this is like, this is there only for a single modality. That means like, because they are specifically trained for images and text, when you give some audio clip, you cannot generate a corresponding image for that. So that is the problem with these types of models. And the reason I've specifically like kind of like highlighted this clip model is, so this is a work that has influenced this ImageBind method quite heavily. So to briefly go over this model, so this CLIP basically stands for Contrastive Language Image Pre-training. So what they do here is, you have images and corresponding text pairs here as the data set. And you have a separate image encoder and a text encoder, which would give you image embeddings and text embeddings. And you essentially try to maximize the cosine similarity between the correct image text pair and minimize the cosine similarity between the incorrect pairs in the entire data set. So that is basically like the contrastive learning concept used here. And so for the text encoder, they use a transformer, and then for the image encoder, they use a vision transformer. And so that this is basically what they do here to like obtain a joint like embedding space between text and images. And next, so there is, yes, you need paired between text and images, yes. And then there's another paradigm which is called multimodal learning. So in this, they try to have different modalities in addition to just image and text. So one example is this work called audio clip. Here, so you have the clip model, they just attach another head like for audio data. So it follows the same contrastive learning method and same like it has the same style here. But the problem here is like now for this model to learn relationships between audio, text, and image, you have to have paired data with each of these modalities in order to find these similarities. So that's the main problem with previous multimodal learning. They explicitly required paired data between all the modalities. And now another some work that shows the power of like joint embedding spaces and the importance of feature alignment, especially coming from clip-based models. So there has been work. When it comes to like segmentation, for the application of segmentation, you can use this clip-based model. So you need like a very small modification. So you have your images and your corresponding text. So here, instead of just embedding and encoding the entire image, they encode each pixel of the image and then find the similarity between the text and each pixel's embedding. So that way you can achieve the segmentation task. And also for 3D recognition, they've again used a variant of the clip model. So here, when you're given a 3D point cloud, you project it into like 2D depth maps as shown here. And then now they are, now because they are 2D depth maps, they are essentially just images. So you can use like a slightly modified version of the clip model again to align these image depth maps with the text so that you can use it to recognize 3D objects. So this shows, these are like prior work that shows the power of embedding spaces, that even though the initial model was looking at just images and text, you can go beyond and do certain other downstream tasks as well. And there's this work specifically called the multilingual neural machine translation. So this is so far the only work that is at least quite similar to ImageBind. But here it's considering only language. So what this model does is like, what this model does is like, in this example, it's trained for English and Korean language. It's trained to do translation between English and Korean, and also English and Japanese language. So when this model is trained in this way, so it's learning an embedding space such that, so here on the left side, it's they have projected the embedding space onto a TSNE map here. And so when you look at this, so each of these clusters means different sentences. So when you specifically look at this sentence cluster here, and when you zoom in, you can see that all three languages, the translation for this English sentence in the other two languages, basically they fall on to the same cluster. So this means like, even though the model is trained for English and Korean and English and Japanese, so given a Korean sentence, that means it can basically give you the corresponding Japanese sentence for that. So that is, so this shows that, basically this shows that you're training with two different modalities, but then if you can learn a specific joint embedding space, you can go back and forth between languages that's where the model was essentially not trained for explicitly. So now that we've gone through the literature of this multi-model alignment and feature alignment and the power of like embedding spaces, let's move on to their method. So like I mentioned before, they are focusing on the binding property of images. So their core is an image. And they're also looking at videos. But then when it comes to videos, you can break it into frames. So essentially that would also result in images. So this is their core space. And then they're looking at the other types of data like depth, thermal, IMU, audio, and text data. IMU is so inertial measurement unit signals. They have accelerometer and gyroscope signals, which gives you like the acceleration across the 3 axes, and also the pitch roll yaw. That's like the angular acceleration along. So it's like the 6 sensors. Yeah. So yeah. So now you have your images and you have all these other data. So what they're trying to do is they are going to align each of these data with images. So here it's easy to align text, depth, and thermal with images. So they are basically taking the features of images and the features of these text, depth, and thermal data and align them. And for audio and IMU data, they extract features from those 2 modalities and then align them with the features, video features, which is also basically very related to images when you break them into frames. So the model is trained to do exactly this. So they show that once you train this through experiments, they show that this model is able to align the other data modalities, even though it's not explicitly trained for them. Because of this, so they term it as emergent alignment, because the model was not trained to do that, but it's appearing in the performance of that model. So for this, when it comes to data, all you need is paired data with images, and they actually don't need to come from the same images. So that's why there are 5 different data sets. You just need paired data with image, so image text paired data, image depth, video audio, image thermal, and video and IMU data. So none of these, when you look at the images, none of them actually have to have the corresponding data coming from text, depth, audio, thermal, or IMU. So they're just separate pairs of data. So now if you look at their architecture, now you have your image and you also have your videos. So what they do is like they break videos into 2-frame video clips. So then you have like a series of images, and you use an encoder to get features of these images. And basically they use the vision transformer here coming from the clip model, because the work from clip have shown that they have really strong feature representations when it comes to images. And then they have audio. There are 2-second audio clips. Without considering them as like time series signals, they convert it into Mel spectrograms. So Mel spectrogram is basically like a time frequency plot, but in the Mel scale. So now this is again an image. They would use a different vision transformer to encode this audio data. Similarly, you have thermal images. They treat thermal images as one single channel images, and they use another separate encoder to encode thermal data. And then you have depth images. Depth images, the original data set, it has RGB and depth information. So instead of using all those channels, they convert it into like a disparity map. Disparity map is like, it's basically like a black and white image, which would have where each pixel's intensity shows the depth of the object there. And so again, now this is also then a single channel to the image, and they use a separate encoder to encode the features of depth. And for IMU, because IMU data, so as I explained before, it has accelerometer and gyroscope signals. So coming from XYZ axis, and there are 6 time series data there. So they would first use a 1D CNN to encode it. That's like a first pre-stage encoding. And then they would send it through a transformer to get the final embedding that represent IMU data. And then finally, they have text data. They would again use a text encoder. For this also, they will use the encoder coming from the clip model to get the text features. And then for each of these embeddings, they send it through a linear projection head, which is modality based. That's why they are like separate. I've shown them separately here. And they would get a fixed d-dimensional vector representing each of these data modalities. So once you get these d-dimensional vectors, they would use the contrastive objective shown here on the right to train this model, so that finally they would come up with this joint embedding space. So when you look at this loss, just like how I explained in the clip model, so say that you have your ith image, and then you have the corresponding ith observation for the M modality. you would encode it using their respective neural networks, and then you would send through this loss. So what this loss would do is it would here on the top, it's finding the similarity between the correct pair, and then you have on the here you have to basically you're finding the similarities between the correct and incorrect pairs in addition to the correct pair, and then you're maximizing the similarity between the correct pairs and minimizing the similarity between the incorrect pairs. So using this loss, this is what's used in contrastive learning. Um, so when you use this in your embedding space, you would get like a good embedding space, which would have similar features coming from different modalities, basically clustered together. So this is just, so they use it as a symmetric loss. So they do this for both IM and then MI. So once this model is trained like this, they show the like they mostly focus on showing the zero-shot applications of this model, which basically shows how that even though you train these for image pairs, data coming from images, that they have connections with the different other modalities as well. So the first experiment they show here is the imagined zero-shot classification. So to clarify the terms a bit, so a zero-shot classification is, so from an example, it's like a model trained using only audio and text pairs, but then during inference, it can actually classify audio that's coming from unseen classes, but using the text prompts that you use for training. So this is called zero-shot classification. Emergent zero-shot classification means it's a model which is not explicitly trained with audio and text paired data. It is trained on image and text and image and audio pairs. And eventually, when you send in audio and text prompts, you can basically do a classification of the audio signals. So that is what emergent zero-shot classification means. So yeah, when you look at this table, they show that this model is quite good for emergent zero-shot classification. So you have to look at the results here, shaded in blue. So when you look at, so the bottom row shows the results of the supervised learning results for each of these tasks. And then basically when you give text data here, and when you have depth data, here they've been able to classify the depth images correspond to the using the text information here. So they've looking at here, so for different data sets, they've got, I think, like it looks, they claim that it's excellent results. So I think like there's still room for improvement here, but then since they are not explicitly trained to classify either depth images or no audio or thermal or no IMU, I think it's quite good when you look at the results compared to the other learning methods that explicitly use text images, text and yeah. Oh yeah, so they are all top one accuracy, except for MSR VTT. Here they use recall, and for audio, so this AS-A, here they use the mean average precision. So that except for those two, everything else is top one accuracy. Yeah. So from these results, they basically try to show how that 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 the text um, uh, that how it implicitly transfers the text supervision associated with these images to other modalities that are uh, that are image based as well as non-image based like audio and IM. And then next is show zero-shot text-to-audio classification and retrieval. So for audio retrieval and audio classification, so they have got so far they have got the best results compared to the other like kind of like clip-based models which already has audio and text pairs to do this task of zero-shot audio retrieval. They have obtained good results. And so from these results, what they try to show is that it basically validates the ability of this model to align audio and text by using images as a bridge. And then next, again, so here in this experiment, they've basically taken the audio and depth encoders from their model and used those encoders to do classification. So in blue here is the audio encoder coming from ImageBind. And so as you can see that they have obtained quite good results compared to audio MAE, which is a model that specifically uses audio and text to do the classification. So here, compared to that, their model has, I think, huge gains when it comes to do the classifying audio, which is better for even compared to the supervised method when you have like less than 4 shots per class. And then there's like a similarly huge gain between their depth encoder and the multi-MAE model, which explicitly uses depth and text data to train that model. So what this experiment shows is that their encoders, even though they are used to align with image features, the features coming from these encoders can basically generalize to do other classification tasks that's specific to that data modality. So I think here few shot classification means you have very limited examples coming from that class. And so when you are given different, like totally new audio clips, it's still able to classify those audio clips, even though it's like it had very limited data. So I think, so zero shot means there are no examples from those for those classes during training, but it's able to classify those audio clips during inference. Yeah, so it's like, I think like, so the audio comes from a class that you've never seen before, but you have text prompts that's related to those classes. So basically it can, like, I think predict the class of that audio that's mostly related to with the text that makes most sense about that audio clip. That's what I felt. Yeah. So similarly, I think like 1, 2, and 4 shots means like, I think probably like the number of examples that it had during training. And yeah.
Under the zero shot, there's like a reference prototype, like during inference. So even though the model has not been trained to see those examples, during inference time, there's a like prototype like sample that we are So otherwise, if the inference are a bit confused, like how it makes the prediction.
Yeah, I think like, so there are like, there are different texts, the prompts, right? So I think it's trying to classify that audio clip which is closest to that text prompt. I think that's what it is. But that audio clip is like, it's quite different from the existing classes, but it could use like a combination of words that would essentially classify this audio clip. That's what I felt like makes. Yeah, they're different.
No, so train the classifier. You said that there are 100 classes, but for some classes you don't have any training. So
Any training paired data, yeah, but that like that class word might be there in the text, but it's like not paired with any image. That's right, because here they give text, like not explicit like words like ball, door, not that. They could that's a blue ball, that's like the text given to the model. So yeah.
This audio and classification is like audio classification. Like, is it like an audio clip and like what are we going to classify it?
So I think you have a specific sound in the clip, and then you're trying to, yeah,
Type of
basically describe like what that is. Yeah.
one depth also.
For depth also, I think
Using
that,
depth images,
yeah,
maybe classifying class.
maybe classifying the, yeah, something like that. Yeah. Trying to basically describe what's seen in that. Yeah. Yeah. And so here, this is another application that they show in the application of their model. So given audio samples, they are able to retrieve images and videos. So this has a direct link, right? Because audio and images are what's been trained. But then see that even though there is no direct link between audio and depth, given the sound of crackling of fire, they are like able to get depth images of fireplaces. And here baby cooing means, so here they are able to retrieve depth images showing cradles. And then similarly there, when you're given the sound of crackling fire, you get similar text prompts out of the model. So that's what cross-model retrieval is in this case. And then another nice application of this model is like, because now there is a joint embedding space, they basically some like compose information using different modalities and get different like images out of the model. So here, like the composed embeddings, basically it naturally has like the semantics from coming from different modalities. So that's why you can ultimately like get an image that would have the features of these input embeddings. And another task is like this object detection with audio queries. So it's like there are models which where you can give text prompts, and then it's able to segment the object that's relating to that text prompt. So here, what they've done is they've removed like the text encoder from those models, and they've attached their audio embeddings there. And when given their audio embeddings, those models are able to like segment objects corresponding to those audio clips. And finally, audio-based diffusion models. So this for this, they've used that DALI, and they basically replaced DALI's text prompts with audio embeddings again. And so given some audio clip, that model is able to like retrieve, generate an image that would describe what's in the audio clip. So basically, so this they've been able to train a joint embedding space using only image alignment. And when you use data which pairs with only images, their model is able to like have this emergent alignment across all the other different modalities. And so here, contrastive learning is used only with image where they pair image features with different modalities. Instead, if you could have alignment data between each of the other different modalities, they claim that their embedding space would improve. And finally, so these models, it's not specifically trained for some downstream tasks, so it's always their performance would be lower than its corresponding specialized models. So that's about it when it comes to ImageBind. You could find their paper in this link, and also their GitHub. They have open sourced the code, and there's also a demo page for this project. So if you have any questions, I'd be happy to answer. Yeah.
I think like it can
Yeah, that's what even I was thinking, like, even this application, I don't know how crazy that idea is, but like we're here, so once you have like a joint embedding space, so here they've like basically done arithmetic with the embeddings to get something out. So like if we have, for example, images and maybe certain protein related data, if you could like at the embedding space, if you could combine them and generate something that we want, it would be yeah, it's
people pair.
you need at least paired data at least with those images. It doesn't have to be the same images, but then still it needs data. Yeah. And the models are all transformers, so it's quite big. We need a lot of data, I think. Yeah. Or we could use use this model as like a pre-trained model and then see if it would be able to generalize, but I'm not sure, yeah, how successful that would be given the feature space of the data that we are working with.
The data set is like.
Yeah. Yeah.
These are like all open source.
So the web data is, I think the others are also probably open source data. Yeah.
So the next slide. In the next one. So
Yeah.
I get that image encode is from straight image and expand last one also. But the audio encode, those are like trained based on those data sets, right? I mean, so like how is the encoder, for example, trained?
So they use a vision transformer. I think like they use like an off-the-shelf vision transformer. I can't remember exactly which one. And then they like train those architectures from scratch for those data.
So that image and thermal is so straight, like the previous slide you mentioned.
Oh yeah. So these encoders, they will basically give you the features out, and then they are trained. So they have the image and thermal data. They are the paired. That's the pair, right? So they would use this contrastive loss basically align the features coming from these two encoders. Yeah. So within this, so for a given pair, you have the correct image and thermal pair. And this contrastive loss should know to like basically help them cluster those two together and then push away the other thermal images from the image. Yeah.
So like when training, we are using different data sets and different modalities.
Yeah. Yeah.